Right, question 1.5 is asking you to work out what the distance is required for this barrier to bring this colliding car to a stop. It tells you the force that the barrier generates as a function of the distance from the initial impact. So in this example, unlike the previous example I went through, question 1.2, the force is varying and it's a function of position. So let us just remind ourselves of the lecture notes, which tell us that the work done is equal to the change in kinetic energy, and this is our general expression for work done. So when the resultant force is a function of position, we have to integrate it over the path that it's acting. Okay, so let's go back to the question and draw a bit of a diagram. So we've got it's my picture of a car at the position when it hits the barrier, and then here's the car again once it's stopped, and I'll call that position 1 and I'll call that position 2, and in the question it says that S is the distance from the initial impact. So when S is equal to D, we're in position 2, and that's when it stopped. So D is the total stopping distance, and that's what we're trying to work out in this question. So what we'll do is we'll just write down the main result of the lecture, which is from lecture 1, which is that the work done between these two positions on the car is equal to the change in kinetic energy. So the kinetic energy at position 2 minus the kinetic energy at position 1. And you don't have to think about this for too long to realise that the kinetic energy at position 2, once it's stopped, is going to be equal to 0. So this is just equal to minus T1. And we can write down an expression for T1, it's equal to minus half m V1 squared. And I think we get both of those things in the question. We're told, so minus a half times the mass is 2,400 kilograms, there it is, and we are told that this initial speed is 100 kilometers an hour. So, if you want to convert from kilometers an hour to meters per second, just divide by 3.6. And that gives us minus 9.259 kilonewton. 10 times 10 to the 5 newtons meters. I made a bit of a mess there. Sorry about that. Okay. So now what we're going to do is we're going to evaluate. So we know what the work done should equal, because it's got to equal to the negative of the initial kinetic energy. And so let's write down what the work done should be in terms of the integral of the force. So from our lecture, we know the integral of the force. So the resultant force, there is only one force here, so I'll call that F, which is a function of this position S. So we're going to integrate that from S equals 0 to S equals D, which is its stopping distance. And the question, so I've just rewritten that in scalar form basically, and the question tells us that this force function is equal to minus 4,400 plus 50,000 S. And I'm going to do some integration now, because we've just got a very simple function. of s, sorry. So it's got minus 4,400 s minus 50,000 s squared over 2, evaluated between d and 0, and that is equal to minus 4,400 d minus 25,000 d squared. So that's quite simple, and that's going to equal this. So if I take it to the other, so let's just put it over here. That's going to equal minus 9.259 times 10 to the 5. And you might be able to spot that that is a quadratic expression in terms of d. So this is 25,000 d squared plus 4,400 d minus 9.259 times 10 to the 5. So we're going to solve quadratic equation. That's A, that's B, and that's C. And you remember, is it minus B plus or minus square root of B squared minus 4AC over 2A, to give you the roots. Now I've got MATLAB here, so I don't have to do that. I've got a nice simple command that I can type in. So firstly I put in A, then I put in B, 4,400, and then I put in C, 9.259 e to the 5. And this should give us the stopping distance. Well, actually it will give us two values of d corresponding to plus or minus the square root. Okay, so this first one is negative, so this would mean the stopping distance would be over here somewhere, so that's obviously nonsense, so we can ignore this first one. It's this one is the one we're interested in. So our answer is d equals, to three significant figures, it's 6 meters. So that is the solution. Okay.